Okay, let's unpack this. Think about everything happening online right now. I mean, millions, maybe billions of likes, shares, comments, messages, purchases. They're all distinct events, right? Happening every second across these huge systems. How on earth does a computer system keep track of all of them and, tell them apart reliably?
It's a really fundamental challenge when you're building large distributed systems. You absolutely need to assign a unique identifier, a unique tag to each one of those events. And not just events, but also like pieces of data, rows in a database that might be spread out across loads of different servers.
Right. Because if you're using a database that's been scaled out horizontally, sharded, split across multiple machines, that simple trick, the old way of just having one database server automatically count up, like auto increment, it doesn't work anymore, does it?
No, not at all. You've got different parts of your system, maybe in different data centers even, all trying to create these IDs at the same time, completely independently.
So you need IDs that aren't just unique on one machine, but like globally unique across the whole system.
Exactly. Globally unique. That's the baseline.
And often it's not just about being unique, is it? You also mentioned needing something that gives you a sense of time, like telling you when something happened compared to other things.
Yeah, that's often a really key requirement, a time-sortable ID. It's incredibly useful.
Useful, or maybe even essential.
Oh, absolutely critical in many cases. Yeah. Being able to sort events or data by time. It's vital for understanding sequences, for debugging problems, figuring out what happened when, and even just for querying data efficiently, like quickly finding the most recent posts or orders.
It helps you put things on a timeline, basically.
Precisely. Organizes the chaos along a timeline.
So today we're doing a deep dive into this whole fascinating world generating unique IDs at scale in distributed systems. We've got some sources here that look at why it's so tricky, what makes a really solid ID system, and some of the clever ways engineers have figured out how to do it.
Yeah, and our mission really is to cut through the jargon, pull out the main ideas, and give you a clear picture of the different strategies and, importantly, the trade-offs involved in creating these digital fingerprints.
Okay, sounds good. Let's kick things off with the basics, the fundamental requirements. If you're operating at this kind of scale you mentioned, maybe billions of events a day, what absolutely has to be true about a good ID system?
Well, based on the sources, there seem to be four main things. First, and this is absolutely non-negotiable, uniqueness. Every single event, every row must get its own distinct ID, period. No duplicates allowed.
Yeah, I can immediately see why that's number one. You definitely don't want two different payments having the same ID or two orders. Nightmare scenario.
Exactly. So uniqueness first. Second is scalability. The system just has to handle the sheer volume. We're talking like the ability to generate at least 1 billion unique IDs every single day. That's a huge number of IDs.
A torrent, yeah. And it needs to keep up, right? Which I guess leads to the third point.
Right. Availability. The ID generation system has to be up and running, ready to give out an ID whenever an event happens. Even if millions of events are flooding in within milliseconds, it can't become the bottleneck slowing everything else down.
Okay. Unique, scalable, available. What's the fourth?
The fourth, which is often very practical, is for the ID to be a 64-bit numeric ID. That size gives you a massive range of numbers, enough for many, many years of operation. And it's just a convenient standard size that fits well into programming languages and, crucially, database primary keys.
Makes sense. Easier to work with, probably faster for indexing and databases too. Okay, so unique, scalable, available, and 64-bit numeric. That's our target. Now, let's look at an approach that often comes up first, maybe as a contrast. The sources mention UUIDs, universally unique IDs.
Right, UUIDs, they're typically 128-bit numbers, so already not quite hitting our 64-bit target. Mm-hmm. But the idea behind them is very appealing for distributed systems at first glance. Each server, each node, can generate a UUID completely on its own. No need to talk to anyone else.
So that sounds amazing for scalability and availability, doesn't it? If one ID generating server goes down, the others just carry on.
Exactly. That independence is a huge plus.
And because it's a 128-bit number, the chances of two different servers accidentally generating the exact same UUID must be incredibly tiny, right? Like astronomically low.
That's the key point. The probability is extremely low, so they scale well, they're highly available, and collisions are very, very unlikely in practice.
Okay, in practice, probability. I sense a but coming. Where do they fall short compared to our ideal list?
Well, like you said, first off, there are 128 bits, not the 64 bits we often want for, say, database primary key efficiency. Using larger keys, especially if they end up stored or indexed as strings, can slow down things like database inserts.
Right, performance hit. And you keep using words like probability and unlikely. While the chance is super low, it's not actually zero, is it? You can't guarantee uniqueness deterministically without some kind of check or coordination.
Precisely. There is a theoretical, albeit minuscule, chance of a collision. And maybe the biggest issue for many applications. Standard UUIDs, the common versions anyway, are not generated in a way that makes them time sortable. They don't increase monotonically over time. Their value doesn't reliably tell you anything about when they were created relative to others.
Okay, so UUIDs, great for easy scaling, high availability, very low chance of collisions, but they miss on the 64-bit size, the absolute deterministic guarantee of uniqueness, and crucially that time sortability. So what's another way people tackle this?
Well, another approach discussed is something called the range handler. This actually introduces a bit more coordination. You have a central service, maybe a specific microservice, whose job is purely to manage and hand out blocks or ranges of IDs.
A central service. Okay.
Yeah.
Like it keeps track of chunks of numbers. Say, okay, server A, you can use IDs from 1 million to 2 million.
It's exactly like that. A server out in the system needs IDs. It asks the range handler, hey, give me a batch. The handler says, okay, here's the range from 5 million to 6 million. It records that this server now owns that range, and then that server can just use those IDs locally, nice and fast, until it starts running low and asks for another range.
Okay. But a central service sounds like a potential single point of failure. How do you make that robust?
Good point. You absolutely need to. The state, which server has which range needs to be stored reliably, probably in some kind of replicated database or storage system, and the range handler service itself. You typically run it with a failover setup, like a hot standby ready to take over, load the state from the replicated storage, and keep handing out ranges if the main one hiccups.
Right. Redundancy. Okay, so this range handler approach with its coordination, how does it measure up against our 4 requirements?
Well, this approach can actually meet all 4. It's unique because that central handler makes sure ranges don't overlap. It's scalable because many servers can request ranges, maybe not simultaneously from the exact same handler instance, but the system overall can scale. It's available in the sense that individual servers, once they have a range, can keep generating IDs even if the handler is briefly down or slow. Requesting a new range might block, but generation continues locally, and you can definitely set it up to generate 64-bit numeric IDs.
Okay, so it seems to tick all the boxes. Unique, scalable, available enough, 64-bit numeric. What's the catch? There's always a trade-off, right?
The main trade-off here is the potential for wasted IDs. Imagine a server requests a fairly large range, maybe 1 million IDs, and then it crashes or gets shut down before it uses all of them.
Those IDs it was holding? They're just gone, lost from the system until that server maybe comes back.
Pretty much. They're allocated but unused, creating gaps in your overall sequence. You can try to reduce this waste by giving out smaller ranges, but...
Yeah, but then the servers have to go back to the central handler more often, right? Which increases the load on that handler service.
Exactly. It's a tuning parameter. You balance the risk of wasting IDs in large chunks against the frequency and load of requests hitting your central range handler.
Okay, interesting. Range handler uses coordination, meets the core needs, but risks wasting IDs. Now, let's circle back to something you mentioned earlier, causality. Why would we want the ID itself to maybe tell us something about how events relate to each other, not just that they're unique?
Right. Sometimes just knowing an event is unique isn't enough. Systems need to understand the happen before relationship. Think about a comment and a reply. The reply depends on the comment. It logically happened after it. They have a causal link.
Right. Unlike, say, me posting an article and you uploading a photo around the same time. Those are probably concurrent. Neither caused the other.
Precisely. And knowing this difference matters. For instance, in a key value store using a last write wins strategy to resolve conflicts, you need to know which write really was last. Or, in some industries, like finance, there are strict regulations. The sources mention MiFID, requiring traceable clock synchronization down to, 100 microseconds of UTC.
Wow, that precise.
Yeah, to reconstruct the exact sequence of trades across potentially many different systems. The IDs and their associated timing or ordering become crucial for that level of auditing.
Okay, so the ID could potentially help establish this causal order. What about the simplest time-based thing? Just using the millisecond UNIX timestamp. It's a number, it's 64-bit, it relates to time.
You could try it. I mean, a single server using the current millisecond timestamp It could maybe generate 1,000 IDs per second. That's, what, 86.4 million a day? That's a lot, but it's nowhere near that billion per day target we set.
Right, not scalable enough on its own, and it's a single point of failure again. So the obvious next step is to have multiple servers doing it.
Correct. To scale that idea, you'd have multiple servers, each grabbing the current millisecond timestamp. Now, to make their IDs unique across the whole system, each server would need to append something unique to itself, like a server ID, to that timestamp. And you'd stick a load balancer out front to spread the requests around.
Okay, that sounds reasonably simple. Scales better, handles concurrent requests, hitting different machines. What's the hidden trap here? Seems too easy.
And this really gets to a critical point. What happens if two or more different servers, maybe server A and server B, both get requests and generate an ID in the exact same millisecond?
Ooh, right. They both grab the identical millisecond timestamp. They each append their own server ID. Wait, if they just combine timestamp and server ID, could they end up with the same combined value if the events hit different servers in that tiny window?
Not quite the same value if the server IDs are unique, but you haven't actually guaranteed uniqueness for the event itself just based on time down to the millisecond. More importantly, what if the system needs even finer granularity? Or what if clocks aren't perfectly synchronized? The simple timestamp plus server ID approach. It can break down under heavy concurrent load across servers, especially if you need strict ordering or uniqueness within that millisecond. It often fails that fundamental uniqueness requirement in high concurrency scenarios.
Okay, so simple timestamp plus server ID isn't robust enough.
Got it.
This brings us to something like Twitter Snowflake, right? Which seems designed to handle exactly this kind of thing by being more structured.
Exactly. Twitter Snowflake is a really well-known example of generating 64-bit, unique, and roughly time-sortable IDs using a more composite structure. It cleverly packs different pieces of information into those 64 bits.
Okay, how does it break down that 64-bit number? Walk us through the parts.
Sure. So first bit is just a signed bit, always set to 0, so the ID is always positive. Easy enough. Then the next 41 bits are dedicated to a timestamp. Now, it's not the standard Unix epoch. They use a custom epoch, a starting point in the past. For Twitter, it was November 4, 2010. Using 41 bits for milliseconds gives them something like 69 years worth of IDs from that date before that timestamp part would theoretically roll over.
69 years. Okay, that's pretty decent headroom. So 41 bits for time since their custom start date. What's next?
After the timestamp, the next 10 bits are used for a worker ID. This uniquely identifies the specific machine or maybe even the process that's generating the ID. 10 bits gives you 210, which is 124 unique worker IDs. That's usually plenty to represent different data centers and the individual machines within them.
Right, so you know when, roughly, and where, which worker the ID was made. What are the remaining bits for?
The last 12 bits are for a sequence number. This is a simple counter, but it's local to that specific worker, and it only counts within a single millisecond. It starts at 0, and for every ID requested from that worker in the same millisecond, it just increments. 12 bits means it can handle 212, or 496 unique IDs per worker per millisecond.
Okay. So, custom timestamp plus worker ID plus sequence number within that millisecond on that worker. That structure seems to solve that problem we just talked about, two different servers getting the same timestamp because their worker IDs would be different, right?
Exactly. That's the core idea. The timestamp gives you the rough time ordering. The combination of timestamp and worker ID ensures uniqueness across different machines down to the millisecond level, and then the sequence number handles uniqueness within that millisecond on that specific machine.
What happens if one particular worker gets absolutely hammered? Like more than 4096 requests hit it in the same millisecond. Does it just fail?
No. The typical strategy described for Snowflake-like systems is pretty clever. If the sequence number counter hits its maximum, 4095, within a millisecond, the worker simply waits. It pauses generation until the next millisecond starts.
It just stalls for a tiny fraction of a second.
Exactly. When the next millisecond ticks over, the timestamp part of the ID increments naturally, and the sequence number resets back to 0. This guarantees uniqueness, even under these intense microbursts.
Heating a millisecond, that seems like a pretty small price to pay for guaranteeing uniqueness during a sudden flood of requests on one machine.
It usually is. And this Snowflake approach gives you some really nice properties.
Yeah.
The IDs are inherently time sortable. Mostly, because the timestamp is the biggest, most significant part. It's highly available because you have lots of independent workers. And it's deterministically unique if the workers use that wait for the next millisecond strategy during bursts.
Okay, sounds pretty solid. Are there any downsides or quirks to the snowflake approach?
Well, one thing that sometimes comes up is the idea of wasted ID space, or gaps. If a worker sits idle for, say, a whole second, the timestamp part of the potential IDs effectively jumps forward by 1,000 milliseconds when the next request comes in. All the potential ID combinations for those silent milliseconds are just skipped.
Ah, so the generated IDs are time ordered, but the sequence isn't perfectly dense or contiguous. You don't use every single possible 64-bit number from one upwards.
Exactly. You'll have gaps corresponding to quiet periods. The IDs you get are ordered correctly by time, mostly, but it's not a perfectly sequential counter across the entire 64-bit space. It's a practical design.
Makes sense. Okay, so Snowflake gives us time sortability, which is a kind of weak causality, right? Just ordering. What about those systems you mentioned that aim for stronger causality, really capturing that happened before relationship?
Right, we touched on logical clocks. There are things like Lamport clocks, which use a sort of synchronized counter. More powerful are vector clocks. These use an array of counters, basically one counter for each process involved. By comparing the arrays, you can definitively say if event A caused event B, or if they happened concurrently, independent of potentially skewed wall clock time.
Vector clocks sound powerful for understanding dependencies, but the sources mentioned a drawback.
Yeah, the big one is size, that array of counters in a vector clock. As your number of processes or nodes grows, that array gets bigger and bigger. It pretty quickly blows past our desired 64-bit limit for the ID itself.
Okay, so vector clocks are great conceptually for causality, but often impractical if you need a fixed size 64-bit ID. Any other approaches mentioned for strong causality?
Well, the sources bring up Google's TrueTime API, which is used inside their big distributed database, Spanner. It takes a different philosophical approach to time. Instead of trying to give you a single precise point-in-time timestamp, which is really hard to guarantee across a distributed system, TrueTime gives you a time interval. It says, okay, the true time is definitely somewhere between time X and time Y, where X and Y account for clock uncertainty and network latency.
A time window, not a point. How does that help?
By reasoning about these time intervals, systems like Spanner can make really strong guarantees about transaction ordering. They can achieve what's called external consistency, meaning all transactions appear to happen in a single, definite global order, as if they ran on one machine. It essentially bakes strong causality reasoning into its core time mechanism.
Wow, okay. That sounds complex but powerful. So if we sort of step back and look at all these options against our list, unique, scalable, available, 64-bit, and maybe this causality aspect, how do they compare?
Well, if you map them out, like the sources sometimes do in tables, basic UEDs fail on 64-bit, deterministic uniqueness, and time sortability. The simple timestamp plus server ID approach fails on uniqueness under concurrency. Vector clocks are great for causality, but usually fail the 64-bit requirement.
Okay, what about the others?
The range handler can hit the main four, unique, scalable, available 64-bit, but the ID itself doesn't inherently tell you much about causality or time order. Twitter Snowflake also hits the core four and provides time sortability, which gives you that weak causality, that ordering. TrueTime, in the context of Spanner, is presented as meeting all those requirements, including enabling strong causality reasoning, though it's part of a much larger specific system.
It's really clear there's no single best answer, is there? It's all about what you prioritize and what trade-offs you're willing to make.
Absolutely. It's classic engineering. You're constantly balancing things. Preventing duplicates is usually job one, but then you have to decide, is probabilistic uniqueness, like UIDs, good enough? Or do you need the certainty that comes with coordination, like range handler or Snowflake?
And we saw that key length matters too. Bigger IDs might be easier to generate uniquely, like UUIDs, but they can hurt database performance, especially with indexing. You want it big enough, but not ridiculously big.
Right. And another subtle point is guessability. Sometimes, like maybe for order IDs or invoice numbers, you don't want the next ID to be easily predictable. It might reveal business information. So some systems might intentionally add a bit of randomness, but that can make generation or sorting a bit more complex.
Yeah. And thinking about how they work fundamentally, we saw timestamp-based approaches like Snowflake and the simple timestamp idea, and counter-based ideas like the sequence number in Snowflake or the range handler. Any general thoughts on counters versus timestamps?
Well, locally incrementing a counter is usually super fast, faster than fetching a precise, globally coordinated timestamp. But if you rely solely on a global counter in a distributed system, well, you need to store its state reliably, protect it from concurrent writes hammering it, and it can easily become a single point of failure or a performance bottleneck itself. Timestamp-based methods, like Snowflake, spread that generation load out across many workers more naturally.
Okay. And speaking of counters and sequences, you mentioned something really surprising earlier from the sources about monotonically increasing IDs, the ones that just go 1, 2, 3, 4.
Yes, this is fascinating. Did you know that in some of these massive distributed databases, like Google Spanner again, using IDs that are strictly monotonically increasing, where each new ID is just the previous one plus one, can actually hurt write performance?
Wait, what? That seems completely backwards. Sequential should be simple, fast.
You'd think so. But imagine a database that splits its data across many nodes based on ranges of the primary key. If your IDs are always strictly increasing, all the brand new data, all the latest writes are always trying to go to the very end of the key space. That means they all pile up on the few nodes responsible for managing that final range.
Oh, creates a hotspot. All the traffic goes to one place.
Exactly. You get these hotspots that bottleneck the whole system's write throughput. Using IDs that are maybe time-ordered but not strictly sequential, or even somewhat randomized, helps spread those writes out more evenly across all the nodes handling the data.
Wow. So even a seemingly simple logical sequence can cause unexpected problems at enormous scale in a distributed world.
It's a perfect example of how the rules change when you go from one machine to many machines spread out across a network. Assumptions you make for single systems just don't always hold true.
So wrapping this up, what does this all mean for you, the listener?
Well, it means that generating something that sounds as simple as a unique number turns into this really complex puzzle when you're dealing with millions or billions of events every second happening across potentially thousands of machines, maybe in different parts of the world.
Yeah, we've looked at quite a few different ways engineers tackle this, from the independent but probabilistic UUIDs to the coordinated range handler needing that central service, the timestamp methods that need care around concurrency, and then these clever composite structures like Twitter Snowflake. And we even touched on systems that go further to bake in ways to reason about causality, like using logical clocks or something like true time.
It's really a brilliant illustration of system design, isn't it? Always balancing these competing needs. How do we guarantee uniqueness without sacrificing too much speed? How do we make it highly available without making coordination a nightmare? How much complexity do we add for features like time ordering or causality? And these systems, these ID generators, they are truly the hidden engines humming away behind the scenes of pretty much everything you do online. Every message, every purchase, every bit of data created, it all needs an identity. And the kinds of systems we've been talking about are what make that possible, reliably, and at incredible scale.
Okay, here's where it gets really interesting. Let's leave you with a final thought. Imagine you're designing a brand new system. The absolute number one requirement is you cannot have duplicate IDs, ever. And it needs to scale globally, billions a day, across data centers that might have flaky network connections sometimes. Given everything we've discussed, UIDs, ranges, Snowflake, timestamps, causality, which of these approaches, or maybe a combination of ideas from them, would you start exploring first? And what would be the hardest trade-offs you think you'd have to wrestle with? Something to chew on.